Okay, so good morning. So the agenda for today, I'm going to do a very quick review of unsymmetric loading of thin wall. Then we're going to do about 2 examples. And then from here, it's going to be the end. Okay, so this is the end of shearing stress, okay? Okay, this will be the end of shearing stress. I hope I've made you understand shearing stress with the rules that I've imposed, the 4 rules. Then we're going to start a new chapter, which is stresses under combined loading. So how to analyze structure when we have a complex loading situation. Complex loading, in this case, I mean the structure is under axial loading, is under bending moment, and it's going to go through under torsion. 3 different types of loading, okay, all into one problem. So that's where I'll call real engineering work. So last week on Tuesday, right, we did a condition of symmetry loading, right? So this is a quick recap. So symmetry loading means the deformation is on the XY plane, okay, on the left hand side of the figure, and there's no twisting, right? So there's no twisting of the structure. And when there's no twisting of the structure, then we can apply equation number 1, where stress X is equal to my over I. More important is the equation number 2, where you has Vy over Izz Qz divided by T. And this you can only apply this when a structure has no twisting. And the structure has no twisting is because if we look at the cross-section view, okay, is the loading is symmetry, means the left hand side and the right hand side of the structure on the figure that you see now on the center is symmetry. Okay, so the left side of the figure, so the left and the right are the same. So the axis of symmetry is on your y-axis. Okay, so that is the axis of symmetry. Now, if we are given a case of unsymmetry loading, so if we look at our centroid now, okay, so I'm going to draw a y down here. So this is the position of centroid. The left and the right are no more symmetry. And when that's the case, what you're going to do, or what we're going to observe, we're going to observe a bending in the XY plane and a twist. So rotation, a twist in the about the x-axis. So as I mentioned before, we still want to use this equation. We still want to apply equation number 2. Okay, we still want to apply equation number 2. So the only way to apply equation number 2 without using the shear stress is equal to TR over J. Okay, the only way is to find the shear center. Okay, so that's where we allocate a shear center. So a shear center all over here is a fictitious. It's not there. Okay, I'll tell you this. It's not there. What we're trying to do is mathematically force the shear stress equal to VQ over IT into analyzing a structure that has unsymmetry loading. So the only way to get rid of the twist, right, is to load to position a load at the shear center, okay, which is O down here. Okay, so O is known as the shear center. So we know originally, right, the structure will want to, without the shear center, without, let's say this load, this structure is without the shear center, the structure want to deform in this direction. Okay, it want to twist in this direction. Why twisting in that direction? Because this side of the structure has lower stiffness, okay, than this side, than the right side. So it's higher, so it tends to what? Twist. So the only way to fight the twist is to position a load P on the shear center a distance away, E distance away from the structure. So we have a counter what? We have a counter moment so the structure not twist. So when that's the case, then we can apply shear stress is equal to VQ over IT. Now, this is only true if and only if the structure is a thin wall. In a thick wall, the possibility of the twisting is the possibility of the twisting is less. Now, can you all hear me? I have some students say that y'all can't hear me. Can you all hear me? Anyone?
I can hear you.
Okay. So, Omowa, I hope you can hear me now. Okay. You wrote that you can't hear me. I hope you're okay. Right. So, so, so coming back to where I was, right? So once you have this offset, you untwist the material, then you just have pure bending. Okay, you just have bending on your bending deformation on your XY plane. Okay, in order to do that, we have to find the shear center. Okay, we have to find where the shear center is, and the shear center we start designing. Okay, we start designing the shear flow. Okay, so in the shear flow that we are designing in the thin wall, F is any force vector. So F is the shear flow in. Now I think I'll start in a new on our lecture today because I've not written this down for you guys. Okay. Copy. So over here, F denote the shear force or shear flow in the horizontal direction. Okay. And V denotes the shear flow acting on the vertical web. Okay, right. So from here we are able to find. Okay, from here we are able. So we're going to take moment, right? So we're going to take moment about the centroid or about point C, and then from there we can find the shear center. So I'm going to do an example on this. Okay, I'm going to do an example of how to find the shear center. Before I go on, anyone any questions, please? Anyone? Nope. Okay, so I'm going to do the first example. So we're going to look at example number 1. So you can get this example from the notes or from Avenue. Okay, so this is example number 1. Okay, let me get the figure. Okay, so we are going to find, okay, we're going to determine the location of the shear center of a thin wall beam of a uniform section, uniform thickness, having the cross section as shown. So this is our structure. So we have a shear force, okay, coming down in this direction, V, okay. So the solution procedure, I'm going to write for you the solution procedure. So we're going to find the shear center. So we're going to find the shear center. Which is at E, okay. Shear center E. So I'm going to write down the solution procedure. So we have a shear force coming down. So if I have to draw our transformation, this is Y, this is Z, this is rotation about X. Okay, so the solution procedure is still, we're going to find the first moment of area. So for this case is Q is equal to A Y bar, okay, about 8 section. Okay, so I highlight what are these section on later on. Then we're going to apply, okay, then we're going to calculate shear stress is equal to VQ over IT. Okay. Then after that, we are going to locate, you're going to find the force, which we're going to integrate between limits where the shear stress multiplied by the change in area. And then finally, we're going to take moment about point C. Okay, I'm going to draw for you where's point C. So this over here is our point C to find the position of the shear center. Okay, so that is our solution procedure. So the formula is still shear stress is equal to VQ over IP. The only thing that you see difference is new, okay, which is nothing spectacular to you guys. You guys are very good in math. Where the force is the integral of the shear stress multiplied by dA. Okay. So as usual, what we always state, the rules still apply. V and I. Okay. So you should note that V and I are constant. Okay. And Q is the variable now. Okay. So first we have to find second moment of area. We're going to find I. Okay. So we're going to partition this section. So we're going to partition it in such a sense that, okay, so this is my AB section. Okay, so I'm going to have it bigger so you can see better. So we're going to have our, so we're going to partition here. Okay, and then we're going to partition here. So it's symmetry, you partition in this way. Then again, our transformation, Y, Z, rotation about X. So the way we're going to find the second moment of area. And we are aware that the centroid is given. The centroid is running on this line over here. All right. So what we want to find is IZZ. Okay, we want to find IZZ because the shear force, the shear force V is acting here. So we know that we are going to find, so that is Vy. So the shear stress is equal to Vy over Izz, right? Qz divided thickness. So from here, we have to find Izz. So we know that once we are locating Izz, so we know that this direction is our width, and perpendicular